Okay, welcome everyone to Zach's seminar. It's my big pleasure to introduce Aline Zanardini from University of Leiden, and Aline will speak about stability of pencils of plane curves.
Okay, thank you. So hello to everyone, and before I start, let me just thank the organizers for the invitation and for the opportunity to speak here today. So thank you very much. Okay, so in this talk, I will be reporting or presenting some results that I obtained as part of my PhD thesis at University of Pennsylvania under the supervision of Antonella Grassi. And here is the outline for my talk. So what my plan is, I would like to start explaining a bit, so what exactly is the problem that I'm interested in, and more importantly, what kind of approach or tools I'm suggesting we use to tackle this problem. And in particular, I want to spend some minutes telling you something about this birational invariant called the log canonical threshold. Then we will move on to the mathematical setup, a bit of notation and what we need, so that I can move on and actually state the main results. And I also would like to illustrate these results with some concrete and simple examples. And in particular, one part of the talk will be sort of an application of these results. We will then focus in the case of, we will focus on certain pencils of plane curves of degree 6, which are called Halphen pencils of index 2. So these are very classical objects. They have been introduced in the 1800s, and there's a very rich geometry attached to it. So this is my plan for the talk. And before I forget, everything is over the complex numbers. Okay. So the problem that we are interested in this talk is the problem of classifying pencils of plane curves, so one-dimensional linear systems of plane curves, up to projective equivalence. And the tool that we're going to use to construct the desired classification space is geometric invariant theory. So the word stability appeared in the title of the talk, and so I have in mind GIT stability. And the general framework of GIT tells us that in order to construct the classification space, the quotient, one needs to determine what the so-called semi-stable and stable points are. So my goal is to present you some stability criteria for this classification problem. And what I'm suggesting is the following approach. The idea will be to obtain criteria in terms of these 3 bullet points. So it turns out that we can relate the stability of a pencil to the stability of the curves that lie in the pencil. We can also relate it to the log canonical threshold and to the multiplicity at a base point. And as I told you in the beginning, I want to say something a little bit about this log canonical threshold that I highlighted here. So, because this really is gonna play an important role. So let's, so here is a definition. So the log canonical threshold is a number that we can associate to a pair x comma delta. So here x is a variety, delta a choice of divisor on it. And this is measuring the failure of the pair being what we call the log canonical. And this, so let's, for the purposes of this talk, let's say x is smooth. And so being log canonical is something about, telling us something about the singularities of delta. And then the smaller this number is, the worse the singularities are. And again, for the purposes of this talk, let us think of this property of being log canonical as the correct or the right kind of singularities one needs to allow in order to construct compact moduli spaces. So this is the definition, and I'm being a bit vague, but I will present a very concrete example in the next slide, and then we're gonna see how to compute it for a curve in the plane. Okay, so let me now just point out the following. So in the beginning, I told you that one of my goals is to relate the stability of a pencil to the log canonical threshold. And in fact, this idea of relating these two notions, it has appeared before, it is known. So we have these results for curves. So in one direction, proved by Hakim and Kingley in 2004, and then in the other direction by Shoutzov in 2017. And later in the talk, I will try to I will present some results that have the same kind of flavor, but for pencils of plane curves. Okay, so let's see just a quick example. Now X is C2, the plane, and I'm choosing this cuspidal curve as my divisor. And okay, so how do we compute? What we want to do is to compute the log canonical threshold of C2 comma delta. So what we do is that so we take a log resolution. I'm calling here mu, and then we can express the quantity in the left that I write here in the equality in terms of the exceptional divisor, Ci. And so these are going to appear with some coefficients. And what we want is to find, if we go back to the definition of the log canonical threshold, what we want is to find the largest possible t such that these numbers, they are all greater or equal than -1, and that's going to be the log canonical threshold. And if you compute it, you find it is equal to 5/6. So in this talk, we will be interested in the log canonical thresholds for plane curves. So so this illustrates how one would go about computing it. Okay, so that's all I wanted to say about this. So this is some sort of introduction. Now I can tell you what the mathematical setup is for the problem we are interested. And first, I'm going to start quite generally, and then I'll apply this to our case. Okay, so let's start with some projective variety X, and let's assume there's some reductive group G acting on it, and let's choose some ample line bundle L on X. So use some power of it to embed it in projective space, and let's also choose a lift of the action on X to the total space of L, which is linear on the fibers. Then we can define the associated DIT quotient, and by definition is this projective variety. Now observe that we have, this comes with a natural map from the quotient map from X to it. But this is only rational, right? So this is not defined precisely on the points where all the invariant sections vanish. So these bad points where this quotient map is not defined is what we called unstable. So, and the opposite of that, so the complement of the unstable points are the so-called semi-stable points. And among the semi-stable points, we have some special points called stable, which are those for which the orbits are closed and of maximal dimension. Okay, so but how do we find this semi-stable and semi-stable points? So we have criteria for that, and it goes as follows. So our group G is acting linearly on X embedded in the projective space. So it means that this action is going to lift to the affine cone. And then we have the following topological criterion. So for if I put a little x in X, and I choose a lift X tilde on the affine cone, then little x is semi-stable if and only if 0 is not in the closure of the orbit of the lift. And little x is going to be stable if and only if the orbit of the lift is closed and its stabilizer is finite. Okay, now let's think about what this means if G is just a multiplicative group. Then the action of G on X is just some finite dimensional representation where the vector space V here it splits as a sum of one-dimensional vector spaces Vi, and it turns out that the analysis of stability, it amounts to looking at the sign of the weight I that appears here. In fact, this is the typical situation in the sense that for any group G, it suffices to look at one-parameter subgroups of G and look at the sign of its weights. And that's precisely the famous Hilbert-Mumford criterion. So this is the let's say the general GIT setup, and I have been talking about an arbitrary X and G, and now I want to apply this to our problem. Okay, so the first observation is the following. So I'm going to consider G to be SL3. So remember, I'm interested in classifying pencils with plane curves up to projective equivalence. And the reason for this reduction for the group here is just because SL3 and PGL3 are going to act with the same orbits. So, okay, so G is SL3, and X is the space of pencils with plane curves of degree D, which I'm going to identify with the Grassmannian of lines in the space of all curves of degree D. Well, then the Grassmannian, in the Grassmannian, there's really just one choice of line bundle, and then we use it to embed in projective space, and that's the Plucker embedding. Now, let's be more precise on what the Plucker coordinates are, and also introduce a bit of notation because I'm gonna need later on. Okay, so I'm going to denote a pencil of curves of degree D by curly P. And then if I choose two generators, so C sub F and C sub G, meaning that I choose some coordinates and then these are given by the zeros of some polynomial F equals 0 and G equals 0. So given that, then the Plucker coordinates, they are exactly all the 2 by 2 minors that like I wrote here in this slide. And the notation for the coordinates throughout the talk is going to be M sub I, J, K, L. Okay. Now, I just told you that one of the tools that we have for the GIT analysis is the so-called Hilbert-Mumford criterion, and it has something to do with one-parameter subgroups of G. So the next thing that I want to do is to tell you how the one-parameter subgroup acts on the Plugger coordinates, and here is what happens. So if I have a one-parameter subgroup which I'm taking to be normalized, then its action on a Plugger coordinate is simply multiplication by t to some exponent, and there's a very explicit expression for that exponent that I write here. So the r sub I j k l, and then and that's how the action goes. And now the next thing I want to do is to introduce an analog of the Hilbert-Mumford weight, but I'm going to adjust a bit the definition. That's because it's going to be useful later. It makes it a bit easier to relate to the log canonical threshold. So here is the definition. So we're going to define this omega. We fix the one-parameter subgroup lambda, and then we're going to define this omega of P with respect to it, and then it's the minimum of D set. Okay. If we do this, then the Hilbert-Mumford criterion can be stated, and the statement is the one that I wrote down here. So a pencil is going to be unstable, respectively non-stable, if and only if I can find a one-parameter subgroup lambda such that is bound, and here holds. And on the left we have this expression involving the omega I just defined. Okay, now observe that the group G, it not only acts on the space of pencils, but it also acts on the space of curves. So I can also look at the stability of the curves that lie on my pencil. And in particular, I can also define this omega for the curves in the pencil. And here's the definition. And then one observation is that we can compare if we fix a one-parameter subgroup, then we can compare the omega for the pencil with the omega for the curves that lie on it. Okay, so what do I mean by compare? So that's going to be a key ingredient for the results that I want to present later. So what I mean is the following. So as a consequence of this, what we can prove is the following. So the first is this proposition. So given a pencil, I choose any two curves on it and the one-parameter subgroup. Then I can bound the omega for P from below by this sum. And I also can show a sort of the opposite. I can also obtain an upper bound as follows. So that's the content of the next proposition. Now I start with a pencil and I choose one curve on it and the one parameter subgroup. Then I can show that there exists another curve on the pencil such that now I have like an upper bound for the omega of P, and it's given by the sum of the two omegas for the curves. Okay. And so this is what I mean by compare omega for P and omega for the curves. And as I just told you, this is a key ingredient for the results that I will show you in a moment. Okay. We also can prove the following, which now it's going to relate the the stability of the pencil to the law canonical threshold, as I promised in the beginning. So, and that's the content of proposition 3 that I wrote here. So if I start with a pencil and I choose a base point on it, then I can show that there exists some one parameter subgroup lambda, and such that for any curve in the pencil, this inequality here holds. And we can think of the content of this proposition as an analog of the following lemma, which has been known, it's well known for curves. So, and we can find it, for instance, in Collar's singularity of pairs. So if I start with a curve in the plane in the one parameter subgroup, then the following bound holds. Okay, so I've showed you the statement of 4 results, and these are the key ingredients, say, to the main results that I want to present next, which really are the stability criteria for pencils of plane curves. Okay. So so now I'll present the stability criteria, and perhaps it's not going to be very instructive, but then later I would like to show you some concrete examples and applications of this criteria. Okay. Here is the first criterion. When combined these 4 results that I just showed you, you can show the following. So if my pencil is semi-stable, respectively stable, then I can show that I have this bound for the law canonical threshold for any curve lying on the pencil and any base point of it. And note that what the bound that appears here is 3/2D, which is it also, I mean, the inverse of it appeared in the Hilbert-Mumford criteria. Okay, so this is the first result. The second one is sort of in the other direction, and it says the following. So first, there's this condition. We assume that the pencil P contains a curve such that its law canonical threshold equals some alpha. So this might sound a bit weird, but for instance, we might be interested in the case where the pencil contains a smooth member. So then we can take as alpha equals 1, for instance. Okay, so we assume this, and what we can show is the following. So if my pencil is unstable, respectively not stable, then the pencil, it has to contain a curve such that its law canonical threshold, it's bounded from above by this fraction here involving alpha. And perhaps I should make a comment that, of course, this has to make sense, right? So this fraction here has to be less or equal than 1. So there's some something hidden here on what alpha can be, but okay. And the next result is so these two they relate the stability of the pencil to the law canonical threshold. So they have the same kind of flavor of the results I showed you in the beginning for curves. So Hackings and Kimley and Chodzov's results. And the next result that I want to show you will relate the stability of the pencil to the multiplicity at a base point. And the statement is the following. So if my pencil contains 2 curves such that if I sum the multiplicity at a point, and that's greater than 40/3, respectively greater or equal, and that point is a base point, then, so if this holds, then I can conclude that my pencil is unstable, respectively not stable. And I have to mention that just for curves, this has appeared in a paper by Schatzovin from 2017, and is essentially the same argument. My only small contribution is just comparing the omega for P with the omega for the curves, and then you get the bound that appears here. Okay, so these three statements are the main results that I wanted to show you today and give you explicit stability criteria for pencils of plane curves under the action of SO3. Okay, so now let me show you some concrete examples, so some consequences of this of these statements. Okay, so here is the first one. You can show that if your pencil, it contains a curve which has the following form, so it's a multiple line and plus some other curve, and that multiplicity of that line is bigger than 2d/3 or greater or equal, then your pencil is unstable, respectively not stable. And just as a curiosity, in the case when d equals 4, so just to be very concrete, when when d equals 4 and m equals 3, it recovers a result by Balico and Oliverio from 1983. So they have studied the stability of pencils of plane quartic. So what I'm saying is that, so you consider this pencil here of quartics, one of the generators is a triple line and another line, and you can take as the other generator any quartic. This pencil is unstable. Okay. And here is another consequence. So let's now assume that the pencil P contains a curve with at worst nodes, singularities. So I'm imposing this condition just because I want to take alpha equals 1. You can think, so let's say P has a smooth curve, or, okay. Then I assume this, what I can show is the following. So if any curve in the pencil contains only points having multiplicity bounded by this quantity here, then I can conclude my pencil is semi-stable, respectively stable. And so let's see, for instance, when d equals 3, so assuming this condition on the pencil P, so let's say it has a smooth curve. If all the curves in P have at worst triple points or double, then I can conclude my pencil is semi-stable, respectively stable. And the last consequence or example that I want to show is the following. So now assume D, the degree of the curves, is less than 6. Now, if my pencil contains a curve that consists of D lines through a fixed point, P, and another curve that goes through that common point, P, with a double point, then my pencil is unstable. And again, this recovers when D equals 4, it recovers a result by Balico and Oliverio, and when D equals 3, this recovers a result by Miranda from 1980. Okay, so so these are some consequences of the criteria that I just showed you, and for the rest of my talk now, I will focus on another application of these results. So I will now shift my focus to these certain pencils of curves of degree 6. But for that, I need to introduce more definitions and a bit of notation. Okay. So the first definition that I want to introduce is that of a rational elliptic surface. So I am gonna say a smooth rational surface Y is a rational elliptic surface if it comes with a genus 1 fibration, which is relatively minimal. So there are no -1 curves in a fiber. Okay, so here's an example, which in some sense it consists of any example. So on the left here, it's my illustration of a pencil of cubics with a smooth member. So let's say we have two cubics, C and C prime, intersecting at 9 points. So this generates a pencil, and in particular, this defines a rational map from P2 to P1, which is not defined precisely at the 9 points where the two curves intersect. And now, if we resolve this so that we obtain an actual morphism, so by blowing up the 9 points, then what we get is a rational elliptic surface. So it fits the definition that I just presented. And moreover, the exceptional divisor over each base point becomes a section of the fibration. So it's in my picture on the right is represented by the curve in green. And in fact, every rational elliptic surface with a section arises from a construction like this. So it comes from a pencil of cubics in the plane. So there's a one-to-one correspondence. And in fact, this one-to-one correspondence generalizes. And what do I mean by that? Okay, is the following. So we have this proposition slash definition that we can find, for instance, in Dogachev and Kilsack's book on the Hicke surfaces. So given any rational elliptic surface, so satisfying the definition that I just showed you, I can find some m greater or equal than 1, and by rational map pi from the surface Y to the plane, so that the following holds. The fibration F is given by minus m times the canonical class, and moreover, F composed with pi inverse is a so-called half a pencil of index m. And but what is the half a pencil? So what it means is that we have a pencil of curves of degree 3m that has 9 base points of multiplicity m. So, and in fact, if I start with such an objective with a pencil like this, I blow up the 9 base points, then what I get is a rational elliptic surface. So that's why I said this one-to-one correspondence generalized. So there's one-to-one correspondence between half a pencils of index m and rational elliptic surfaces of index m. So that's the m appearing here in the proposition. Okay, so let's So for the rest of the talk, what I'm interested is describing the stability of these Halphen pencils when m equals 2. So I'm looking at a pencil of curves of degree 6. So let's see a concrete example when m equals 2. So here it is. So on the left, I'm representing the generators for the pencil. So one is this curve B, which is a triple conic, and the other one is a double cubic, which consists of a conic and a line, and they intersect represented in the picture. So the line is tangent to the purple, to the conic in purple, and the two conics, they are tangent with full multiplicity. Now, if we separate the members of the pencil, so we blow up one of these point 3 times and then we blow up the other point 6 times, then what we get is a rational elliptic surface, y to p1, such that we're going to have exactly one multiple fiber, which consists of 2 rational curves. So in Kodara's classification, it's of type I2, and that comes with, so it's a multiple fiber and it comes with multiplicity 2. And we also going to have a singular fiber of type 3 star in Kodara's notation. So if we look at the dual graph of this fiber, it's the extended thinking diagram E7. So, and the strict transform of my curve B is going to be that curve that I drew in purple there, appearing with multiplicity 3. Okay, so this is to illustrate the kind of objects that we are interested. And the question now is, okay, so what can I say about the stability of these objects? And before I do that, let me just point out Miranda's work. So this was sort of the inspiration for this project. And in fact, I must say that I actually, the way that this project went is actually in the opposite way that I'm presenting. I actually started thinking about these Halphen pencils, and then it turned out I obtained results that hold for more general pencils. Anyway, so we have Miranda's work from 1980, where he describes the GIT stability of pencils of plane cubics in terms of the types of singular fibers that appear in the corresponding rational elliptic surface. And then the part of my PhD thesis was to describe the GIT stability of Halphen pencils of index 2. And again, the kind of statement that I obtained is in terms of the types of singular fibers appearing in the rational elliptic surfaces associated to these pencils. But what is different is the approach. So the way that I obtained this criteria was by relating the stability to the log canonical threshold and the multiplicity at the base point and so on. Okay, so let me show you now what kind of statement one obtains, and so now for the rest of the talk, P is the Halphen pencil of index 2, and Y is it's going to denote the corresponding elliptic surface. And I will present you the stability criteria for P viewed as a point in the space of all pencils of plane curves of degree 6. Okay, and here is the first result. We can show that if the pencil is non-stable, then the elliptic surface Y, it has to contain a non-reduced fiber. And moreover, if the pencil is actually unstable, then we exclude the possibility of the IN star. So then Y contains a fiber of type 2 star, 3 star, or 4 star. And just to remind you, so the non-reduced fibers are the ones that I drew here on the right. And what I'm drawing is the dual graph for the fiber. And then the numbers are just the multiplicities of the components. Okay, and I should, let me point out that if you're familiar with Miranda's paper on the stability of pencils of cubics, then this statement is also true for pencils of cubics. Okay. So how would one prove this such result? So let me try to sketch a proof very quickly. Okay, so in the Halphen pencil of index 2, there exists exactly one double cubic, and you can show that the singularities of that curve cannot be too bad. So it turns out that the law canonical threshold has to be a half. So, and then because of that, we can take as alpha, we can take alpha as equals to 1/2 in theorem 2, which I presented a few slides back, and then I'm recalling here. So remember that the theorem was the following. So we have assumed that the pencil has this curve with law canonical threshold equals alpha, and then we show, well, if the pencil is not stable or unstable, then I can actually find a curve on it such that its law canonical threshold is bounded by this quantity involving alpha. So this is the theorem that I'm referring to, and I'm taking it. So D here is 6, and I'm taking as alpha just a half. Okay, so because of this, then I can, if my pencil is non-stable, respectively unstable, I can find a curve on it such that its law canonical threshold is less or equal than a half, respectively, less. Now, the claim is that the fiber that corresponds to this curve B, it has to be non-reduced. And the reason for that is because, well, you show that the opposite inequality holds for a reduced fiber. So if the fiber F that corresponds to this curve B is reduced, then the opposite holds. Okay, so we know that this pencil, so we know that the surface corresponding to this pencil has this non-reduced fiber F. And now what we remains to show is that if the pencil is unstable, so the inequality for the law canonical threshold of P2, B, it's a strict inequality, then the corresponding fiber cannot be of type IN star. And the reason for that is the following. So one can show that for non-reduced fibers, the law canonical threshold of P2, B is greater or equal than the law canonical threshold of Y, F. And for a fiber of type IN star, the latter, so the law canonical threshold of Y, F equals 1/2. So if my pencil is unstable, then this fiber F cannot be a fiber of type IN star. Okay, so and this concludes the proof. Well, what the statement that we just proved is of the form, so I assume my pencil is non-stable or unstable, and then I conclude something about the types of fiber in the corresponding elliptic surface. And of course, a natural question is, okay, so what about the converse? And here is a sample result, which is actually an if and only if statement, which is quite nice. And so the statement is the following. So one can show that a Halphen pencil of index 2 is unstable if and only if the corresponding surface, it contains a fiber of type 2 star, and moreover, the curve that corresponds to it is unstable. Okay, and in particular, we see that the stability of the curves on the pencil, they play a role in determining the stability of the pencil itself. Okay, so another natural question then is, can we say what the curve B looks like? So can we classify what are the possible plane curves that are going to yield a fiber of type 2 star? And yes, we can. And it turns out there are 5 possibilities for the curve B when the fiber is of type 2 star. So it's either a triple conic or a cubic together with a flex line with multiplicity 3, or 2 triple lines, or a conic and a line with multiplicity 4, or a line with multiplicity 5 and another line. And if you look at this, so these are sestics, and the stability for sestics is known. So the only one which is semi-stable is the triple conic. So in all other cases, B is unstable. And so the corresponding pencil is also unstable. Okay. So to finish, I would like to go over an example of a pencil that yields a fiber of type 2 star in the elliptic surface, and just to show you how really knowing what the curve B looks like helps you determine the stability of the pencil. So it's sort of an illustration of the of the theorem, and then there's also another slide about the case of higher index. Okay, so let's look at the example first, and here it is. So one starts with a smooth cubic C, and we choose a flex point P1 on it, and we'll denote the corresponding inflection line by L1. Then I can choose another line that goes through that flex point, which is tangent to my cubic at another point, say P2. Okay, so what I'm going to do is to choose the following sestic as B. So I take these 2 lines with multiplicity 3, and I take as the other generator my cubic, the cubic that I started with multiplicity 2. So these are the generators, and define a Halphen pencil of index 2, and this yields a fiber of type 2 star in the corresponding elliptic surface. So what we do is that we blow up the point P1 6 times, and we blow up the point P2 3 times. And here in the picture, I'm drawing the dual graph of the fiber, and in purple I highlighted the strict transform of the 2 lines. Okay, so why is this this pencil unstable? Well, what is nice about this example is that the curve B is very simple, so it's just 2 triple lines. So we can choose coordinates in P2 so that the equation for B is just x cubed y cubed equals 0. And in fact, the equation for C is also simple. So it has this form that I wrote here. And because of that, almost all duplicate coordinates are going to vanish. And in fact, the only non-zero ones are the ones that I listed here. And so we have 8, I think. And this is going to make our pencil be unstable. Okay, so now I'm just going to show you exhibit a one-parameter subgroup that makes this unstable. Okay, so I'm using the same notation as before. So AX, AY, AZ are the exponents of T along the diagonal for the one-parameter subgroup. And I'm going to choose them like this, where A is some rational number in this interval. And then if I compute the omega for P with respect to this one-parameter subgroup, it turns out that what we get is 3 times 5 plus 7a, and the coordinate that's going to give me the minimum for this set is the one that I highlighted in green. And then what I do is look at the Hilbert-Manfred criterion. So what I have to estimate is this fraction involving the omega, and it turns out that this is 5 plus 7a divided by 1 plus a. And because I chose a in that interval, this is greater than 4. And the criterion tells us the pencil is unstable. So this also illustrates another ingredient that played a role in determining the stability of a Halphen pencil, which is really knowing what the curve B looks like for certain types of fibers. Okay, and so the next slide, so this concludes the example. The next slide and before the references is just answering the question, okay, so what can you say about other indexes? So we can talk about Halphen pencils of any index M. I told you that, and we can ask about its stability. And it turns out that these two statements here hold. The first one, I can show that if the pencil has a curve such that it has multiplicity at some base point equals 3 times M, then the pencil is not stable. And the second statement is the following. If my pencil is not stable, then the elliptic surface, it has to contain a non-reduced fiber. So the part of that first part of that theorem that we sketched to prove, this holds for any index, and the proof is essentially the same. We just observe that the pencil contains this multiple cubic with multiplicity m, and then we take as alpha 1 over m and do the adjustments necessary, and that's so the same proof works for any index m. So that's another reason why I decided to sketch the proof. And at last, so here are some references of some of the papers that I mentioned throughout the talk. And so thank you very much for the opportunity again, and thank you for everyone who came today and joined and listened to me. So thank you. I'll stop here.
Thank you, Aline. Thank you very much. Thanks, Aline, for beautiful talk and actually very nice slides. I amazed slides are good. Let me press this. Okay. Thank you. And okay, let's ask questions. Let me first ask a question. So basically, this pencil of curves can be considered as divisors in P1 times P2. Yeah, and for example, for this elliptic surface which you describe, in this case, it's you take a resolution of this of this surface. So yeah. Okay, so maybe it's possible also to restate everything in terms of singularities of this surface. I think, yeah.
Okay, so
Because
that's
results already done. You can just restate it. Not. Yeah, I think basically GIT problem can be probably restated in terms of singularities of this surface.
okay.
Yeah.
Okay.
Just a remark, maybe.
Yes. Okay. Thank you. Yeah, I appreciate it.
And another thing, which is actually very related to something we did with friends recently. So, for example, if you consider this surface, it's not Fana. It's some, but except very few special case when it's a pencil of conics. But in this case, this is just Delpezzi surface of degree 5. In this case, you also can speak about, for example, k-stability of this surface, of this Fana variety. But I think in high dimensional case, maybe, for example, you not like for the pencil of curves, but for example, for net of curves or net of hypersurfaces. When you consider low degree case, it's going to be much more interesting, and you can relate it to the k-stability of ambient space, which is going to be in this case. For low degree case, it's going to be Fana. So we, for example, consider one very special case when it's a net of conics. In this case, it's divisor of degree 2, 1, 2 in P2 cross P2, because it's P2. And also you can link GIT with the k-stability of the total space. In this case, it's going to be Fana 3.
Oh, that's very interesting.
Yeah, so I think it may be, but of course, it's only interesting in high dimensions. So when,
yes.
So just a remark. It's probably not a question.
Okay. Yes. Thank you very much. Yes.
And now let's question. So I think Francesca wanted to ask a question. Francesca, do you want to ask a question? Yeah.
Yeah, I just wanted to ask something very naive question. I wanted to ask if this kind of method can be generalized in higher dimension, a very classical question. I mean, can you find some of your techniques can be useful to study stability of pencils of higher dimensional varieties? Do you think it is possible to do this?
Yes,
at least in some simple case. Sorry for the very classical question, but maybe.
No. Thank you for asking. That's a very good point. So I will start answering the question by pointing out that the first result that I showed by Hacking and Kimley and also Shatsov, it like you have to adjust the coefficients that appear in the coefficients that appear in the statement, but it also holds for pencils of hypersurfaces in projective space. And then instead of a 3, I think what appears is n+1, where n is the dimension of the projective space. And then and the same thing holds for the statements that I showed you involving the law canonical threshold. The same kind of statement holds for pencils of hypersurfaces in the Pn. And the bounds are, again, you essentially replace the 3 by n+1, if I'm not mistaken. So this is, yeah.
But maybe to back up Francesca's question, just very first case, I would say consider pencils of quadric surfaces, pencils of cubic surfaces.
Yes.
This especially pencil of cubic surfaces.
Cubic surfaces, yes. I'm actually.
This is actually fun. This is Fana variety. Yeah, if you consider the total space.
Yeah, I haven't wrote down and worked some examples, but I do know that the classical GIT analysis for pencils of cubic surfaces has been done. So you already know the answer. So, and then you could compare and see. So that's very interesting, and I should do that at some point. Yeah.
Any other questions to Aline? Please ask or type in chat, whatever you prefer. Let me check chat. I don't know.
You mentioned that this pencil of cubic surface is already like the stability of pencil of cubic surface is done? Is such
It's
a
done.
work related
Yes,
to like,
I have it in the computer. I just don't remember exactly how to spell the last name of who did it. It's like a Nordic last name, and but I can share it with you if you'd like. But it's done.
Okay.
Yeah.
Thank you.
Very nice. Any other questions? Okay, looks like there are no more questions. Then let's thank Aline again. Let me press here. Okay, Aline, thank you very much. Excellent talk, and yeah,
Thank you.
we'll waiting for your future results. Yeah.
Yes, thank you again for the opportunity and the invitation, and also for the suggestions at the end. Thank you very much.
Thank you very much. Okay, bye everyone. See you next week on the Zach seminar. Bye.